So natural logarithms. Here we go. A natural logarithm, all it is a logarithm with a base of e. And if you remember back previous unit or the unit before, e is that value, that irrational constant that is approximately 2.718, so forth. So if you deal with the inverse function of y equals e to the x, where e is your base, then the logarithm of that, the inverse function of that, is called the natural base exponential function. And it just is written a little bit differently than a regular logarithm. Instead of saying log e of x, we use ln x. Ln just means log with a base of e. That's it. There's nothing special about it. It's just a way. Yeah, you're good. It's just a way of writing it a little bit differently. So anytime you have an ln, you know that the exponential function that it goes with has a base of e. That's what we're talking about. It's sort of like if you have log with no base value, you know it's talking about log base 10. Ln means you've got log base e. And so that's what we'll be dealing with today. So the inverse of a natural base exponential function is a natural logarithm, which can be written as log base e of x. So right there, you could write it like that, but it is more often abbreviated as ln. So ln x, log base e of x, those two things are identical. There's no difference between them whatsoever. Every point of the graph of y equals e to the x is reflected on the line y equals x. You swap the x's into y's, it's the inverse function, resulting in the graph of y equals ln x, or log base e of x. You can write equivalent expressions, equivalent exponential equations using the definition of a natural logarithm. So for example, ln 6 equals x is the same thing as log base e of 6 is equal to x, which is the same, not the same thing, but which is e to the x equals 6. Well, that is the same thing. So which is the same thing as e to the power of x is equal to 6. Similarly, you can write the equivalent logarithmic equation for an exponential equation with base e. So if you start with base e, you end up writing an ln. So ln of the argument is equal to the exponent, just like a regular logarithm, except for using ln as an abbreviation of log base e. It's the only difference. The same properties that we learned previously, all the properties of logarithms apply to this one as well because it is a logarithm. So moving on from here, we are going to write an exponential equation in logarithmic form. So by the way, if you're doing this on your assignment, you do not need this middle step where it says log base e. You can if you want to, but it's not a necessary step to write. So if we're doing this first one here, we're going to have log base e of the argument of 14, which ends up being ln of 14 is equal to x. That's all we got to do. You can skip this middle step. Like I said, you don't have to write that in there if you are converting from exponential to natural log, or if you're going from a natural log to an exponential, you don't need that middle step. We're writing it here just as a way to show that, you know, there is a process to get there. What value goes here on B? What's our argument here for B? X, yeah. So log e of x is equal to the exponent, which is 7, and we can see the 7 needs to go over here anyway. So we're going to write ln x equals 7. So go ahead and rewrite a and b down there in natural logarithmic form. You don't have to go with the log base e middle step if you don't want to. You can go straight to the ln form at the very end if you want to do that way. All right, so quick check here. We're going to get ln of 4x is equal to 3. And over here, we're going to have ln of 3 is equal to 4x. Those would be converting from exponential to logarithmic form or natural logarithmic form. If you have the in-between step, you're welcome to have that on there as well. If you wanted to do it that way, the in-between step would say log base e of 4x equals 3. And here you would have log base e of 3 is equal to 4x, which then would turn into those. Any questions on anything so far? It is the same thing that we've been doing. We're just using ln now as opposed to a log base of something. So ln means log base e. All right. Questions? Cool. Maybe we will get through this today. This is going a little bit quicker than I thought it might. All right. Example 2. We're going to be writing equivalent exponential equations. So in this first one, we've got ln of 9 is equal to x, which means we have log base e of 9 is equal to x. So our argument is 9. We have our base of e, which means our exponent is x. So the answer here is going to be 9 is equal to e to the x. How about b? We have ln x equals 1.7347. We've got our base here of e. We have our argument of x, and we have our exponent of 1.7347. So again, it's doing the in-between step. So log base e of x, this is still 1.7347. So our exponent is here, which means that our base value of e is going to go on the side with that exponent. So it is e to the 1.7347 is approximately the value of x. So try a and b down here, and then we'll keep going. All right. What do we have for A? Volunteer. What do we got? What's our base? What's our base? I think somebody said it. E. What's our exponent? 4. What's our argument? 3x. E to the fourth power equals 3x. That's the answer for that one. For B, what's our base? E. What's our exponent? 3x. What's our argument? 4. E to the 3x equals 4. All right. So it's basically the same as any other logarithm. Using an abbreviation for log base E. We're using ln for that. All right, now we're going to apply some properties of logarithms. This will be a good review because the properties of logarithms are the same as they've always been. So if we take a look here at example 3, it walks us through this first step pretty carefully. And then from there, I'll have you do one on your own after that. So, right. 1/3 ln 8 minus ln 3 plus ln 9 as a single logarithm. Since they all have the same base, we are allowed to use our properties of logarithms here. They all have base E. So, first thing we're going to do is use the power property of logarithms, because if you have a multiplication of a logarithm or a natural logarithm, that's the same thing as the log of the argument to a particular exponent. And so this can end up being the exponent with 8. So we're going to get ln of 8 to 1/3 power minus ln 3 plus ln 9. Now, ln of 8 to the 1/3 power, if you look over here, 8 to the 1/3 power is the same thing as the cubed root of 8. So the number that multiplies by itself 3 times to equal 8, which is 2. A rational exponent, fraction as an exponent, is the same thing as a radical. And so you can take the radical form of 8 to the 1/3 as the cube root of 8, which is equal to 2. So ln of 8 to the 1/3 power, or 1/3 times ln 8, would be the same thing as ln 2. And if you think back to our properties of logarithms, if you subtract logarithms with a common base, that is the same thing as dividing the arguments. So ln of 2 minus ln of 3 is going to be ln of 2/3. Divide the arguments, which ends up being ln of 2/3 plus ln of 9. If you have a common base and you add logarithms, what do you do with the arguments? Multiply. All right. So this is going to be equal to ln of 2/3 times 9. What's 2/3 times 9? Fraction times a whole number, multiply the numerator by the whole number. What's 2 times 9? What's 18 divided by 3? 6. So the answer is ln 6. Now, if you want to, you can check the answer on your calculator. Your calculator has an ln button right underneath the log button. So it's basically to the left of the 4 on your calculator. So if we go with 1/3, so if you go to math, fraction, 1/3, move on over, and then we type in ln 8, and then we subtract ln 3, and then we add ln of 9. We're going to get a decimal for sure. But then we're going to be able to compare that with ln of 6, because we said if we combine these things all together using properties of logarithms, we end up with ln 6. So 1.791, all that good stuff there. We said that if we combine everything, that's the same thing as ln 6. So this should be equivalent to that. So if you type it in, hey, look at that. It's the exact same thing. Cool. That's an easy way to check to see if you've done it correctly. Check your answer with the original. You get the same values, you've done it correctly. So I want you to try the check set. Use the margin on the left to go ahead and work that one out if you need some more space, which you will need more space. So give that one a go. In terms of the math with logarithms, the actual calculations turn into fairly basic math. I'm not afraid to say that word in this case. It is fairly basic math in terms of the actual calculations that are being done. In fact, the more you do these, as with anything in math, the better you will get, and you might end up being able to use mental math to do this. Because as I'm looking at this, I'm kind of messing around with some stuff here, and we get should be ln 14, right? So we got ln 14. So if you take a look here, if we use the power property, I'm going to write this all out in a second, but if you think about the power property, if you multiply any logarithm, natural logarithm or whatever else, that's the same as the exponent with this number here. 27 to the 1/3 power is the same thing as the cube root of 27. The cube root of 27 is 3 because 3 times 3 times 3 is 27. So that's ln 3, this whole thing here. ln 7 minus ln 3 would be 7 divided by 3, so that'd be ln of 7/3. And then you're going to multiply that by 6 because we have a plus here. So 7/3 times 6, 7 times 6 is 42, and 42 divided by 3 is 14. So the answer is ln 14. So you can basically kind of use order of operations in a different way to work your way through this. And, you know, you can get to the point where the more you do this, the more you'll be able to kind of look through it without having to write out everything and do a whole bunch of stuff on your calculators. The more practice you do, you can end up being pretty efficient with this stuff. I will write it out. So over to the side, let's just go ahead and head up here, and we're going to write ln 7. I'm just going to write minus ln of 27 to the 1/3 power. I'll do that first step there. And then plus ln 6. 27 to the 1/3 power, as I mentioned a minute ago, is the same thing as the cube root of 27. The cube root of 27 is 3. So that's ln 7 minus ln 3 plus ln 6. So we use the power rule of logarithms, or the power property of logarithms. And then we just use a rational exponent rule to get ourselves a radical out of that, and then reduce the radical. Now we're going to use the quotient property of logarithms. So if you subtract logarithms of the same base, you divide those. So that's going to be ln 7/3 plus ln 6. And then that means we can take ln of 7/3 and multiply that by 6, because when you add logarithms of the same base, you multiply the arguments. 7 times 6 is 42. 42 divided by 3 is 14. So the answer is ln of 14. Did anybody check that on their calculators? Double check ln 14 against ln 7 minus 1/3 ln 27 plus ln 6. It'll be the same thing either way. Let's see, would that be e to what power is equal to 14? That's a good question. 2 point something or 3 point something? What is it? ln 14, 2.639-ish. Cool. Questions on that? Same process for properties of logarithms that we saw a couple lessons ago. All right. Keep going. I think we will finish this lesson today. That'll be nice. So let's see. Solving. So, because an exponential function with base e is the inverse of the natural logarithmic function, sort of like a function with base 10 is the inverse of a logarithm with base 10, they can be used to eliminate each other. For example, e to the ln x is equal to x. ln e to the x is equal to x. I'll show you off to the side in just a second what that looks like. So if we go over here for a second, and I rewrite, make a little dividing line there. If we go ahead and write this down, e to the ln x is equal to x. If you were to write this in logarithmic form, you would have base e, which is ln, of the argument x equals the exponent. Okay, so anytime you have a base e, you write ln. It's always of the argument, which is x, And that equals the exponent, which happens to be the same thing as that, ln x. So those two things have to be equivalent. If you go from exponential to logarithmic form, you end up with the same thing on both sides of the equation. Okay. Same thing happens with this one. If you go from logarithmic form, ln e to the x power equals x, and you end up writing this in exponential form, we've got ourselves ln, which is base what? Ln is always base e, with an argument of x, with an exponent of x rather, is equal to the argument of e to the x. So if we have a base of e with an exponent of x, it equals the argument of e to the power of x. So we can just use the property of logarithms just to convert between logarithms and exponential functions to show that those things are true. So, given that, questions about how that worked? You can just do that conversion straight, from the two different forms to show that those things are actually equal. So if we take a look here, exponential equations with base e can be solved using natural logarithms because ln e is the same thing as ln e to the first power equals 1. So if you think about how that works, just a second here. So ln e is equal to ln e to the first power, which is equal to 1. This is basically just saying if you have e to the first power, that's equal to e to the first power, sort of like e to the x power is equal to e to the x power. So let's head over and take a look at some actual equations, starting with example 4. All right. So it tells us to solve, and we're going to round to the nearest 10,000. So if you're going to solve for the exponent here, or solve for x, which is in the exponent, you need to isolate your power first. So by isolating the power, that means we're going to get rid of the 8, and we're going to get rid of that -2 that's multiplying by it. So the first thing we need to do, subtract 8 from both sides of the equation. What's -14 minus 8? -22. All right. So -22. We're isolating the power. So that power is still being multiplied by -2. So right here, divide each side by -2. -22 divided by -2 is 11. So just like we had with logarithms, if you have an exponent, a power with an exponent, you could do log on each side. But because we're not dealing with a standard logarithm here, we're dealing with the natural logarithm. Let's put an ln on each side to talk about the natural logarithm. So ln e to the x plus 3 is going to be equal to ln 11. What comes next? Thoughts here. What our next step looks like? Any questions on this or any thoughts on what our next step is going to look like? Ready to figure out what goes here? Anybody? Anybody? No? All right. So the answer is x plus 3. I will show you why off to the side. So the answer here is x plus 3. Now, there's a little bit of a shortcut happening here. But anytime you have a natural log of e to an exponent, the natural log and e are inverses of each other. So these basically undo one another. They're inverse operations, leaving you with just the exponent x plus 3. Now, in terms of how that looks, I can show you off to the side here. If I just rewrite this entire equation, that'll give us ln e to the x plus 3 is equal to ln 11. We know that. Now, if you think about what's going on here, ln is base e. So if we rewrite this in exponential form, ln means base e. ln 11 would be the exponent. E to the x plus 3 would be the argument. Everybody okay with that? ln base e, exponent of ln to the 11, argument of e to the x plus 3. Everybody cool with that so far? So we write this in exponential form. We should get e to the ln 11 is equal to the argument of e to the x plus 3. And anytime, we actually dealt with this in our exponential unit, our previous unit, when we were solving exponential equations. If you have the same base value, what do you do with the exponents? Same base value, what do we do with the exponents? You set them equal. What do we have here? Those are the exponents set equal to each other. X plus 3, ln 11, x plus 3, ln 11. So you'd say ln 11 equals x plus 3, which is exactly what we have right there. So we're basically just using a shortcut because a natural logarithm and base e are inverse operations. You can just take the exponent, those cancel each other out essentially, and you can take the exponent and it will always equal the original exponent of ln 11. So this exponent is equal to that exponent. So these three steps technically are happening in between here and here, but because we have that rule that we saw at the base of page 426, we can go straight from here to here. Are there any questions about that process? This would be a good thing to recognize. Or if you get stuck on a problem like this, feel free to write it in exponential form because you'll be able to get to the same place either way. If you need to take the longer route, please take the longer route. But those two things are absolutely equivalent. All right, now we're going to get, I would actually prefer that we don't write the approximation of ln 11 here. I would prefer us to write equals. So change that approximation to an equals. And also, I want you to get rid of the plus 3 here. Scratch out that plus 3 on the left. The way that I would prefer you to do this is instead of estimating, so my thoughts and my philosophy on rounding is that you should never round until the very, very last step. The earlier you round in a problem, the more chances for your decimal approximation to be off at the end. So don't round earlier in the problem, always wait till the end to approximate. So I'm just gonna write ln 11 here. So ln, and I'm gonna put 11 in parentheses and then minus 3. The reason why I'm putting 11 in parentheses is because you will use your calculator for this last step. And you need to make sure that you put the ln, it's going to open up a set of parentheses. You need to close your parentheses after the 11 and then subtract 3. So If we type in ln 11 and then subtract 3, that will be our answer. And it's going to be about negative point, what are we looking for? Nearest 10,000, so 4 decimal places, negative 0.6021. And that's what we got. And just to be clear, if you typed in ln 11 first and then subtracted 3 from it, it would be the same thing. But my preference is that we always isolate the variable first, then approximate at the end, just in one step, as opposed to doing the approximation and then subtracting after we approximate. So I want you to try this one. Make sure you isolate the power before you apply the natural logarithm to both sides. By the way, when you get your answer, if you want to check your answer, just type it in for x here. 6 times e to the 0.25 times whatever you got for your answer plus 3 should be, it won't be exactly 26 because you approximated, but it should be really darn close to exactly 20. Not exactly, but really, really close. You have any brave people out there who want to give me what they might have come up with? It doesn't need to be exactly right either. If you don't have it right, that's okay. You're still learning. So, anybody? Anybody have an approximation? Negative 6.1347. Finish up. That is the correct answer. So negative 6.1347. Let's see why this works. I'm going to use the margin over to the right. Hopefully you worked out the same thing over here. So I'm just going to write the entire thing to begin with here. So we got 6e to the 0.25x and then plus 3 is equal to 26. All right. What's the first thing we need to do here? First step here is to do what? Divide by 6, but yes, yeah. We need to isolate the power over here, and it's being multiplied by 6, which means we'll divide both sides by 6. So those are going to cancel, which is going to give us e to the 0.25x plus 3 is equal to 26/6 reduces to 13/3. They're both divisible by 2. So 13/3. By the way, if you didn't reduce that, you would still get the correct answer. So if you left it as 26/6, it'll still be the correct answer either way. All right, now that we've isolated our power, what's next? What's the inverse operation of e to an exponent? ln, yeah. That's why we do that, by the way. It's because the inverse operation of multiplying by 6 is dividing by 6. If we want to isolate our exponent here, we need to do the inverse operation of the base value, which is natural logarithm, ln. So we're going to get ln e to the 0.25x plus 3. And because it's an equation, we have to do the exact same thing to the opposite side as well. ln of 13/3. All right, now we saw in the last problem that if you have a natural logarithm and a power with a base of e, those are going to cancel each other out, and you're going to get this exponent here equal to this exponent up here. So ln and e will cancel each other out, inverse operation. So we're going to get 0.25x plus 3 equals ln of 13/3. Now we have 2 steps left. We got to get x by itself. What do we do now? This is turned into a basic equation. What's next? What's our next step in solving for x? No, you all know it. Just need somebody to say it. What is it? What do we do now? Ben, what do we do next? We will divide by 0.25, but we got to get rid of the plus 3 first. Subtract 3. Okay. So subtract 3 from both sides. Minus 3, minus 3. 3's are going to cancel there. That's going to give us 0.25x is equal to the ln of 13/3 minus 3. And then the last thing we're going to do to get x by itself, divide both sides by 0.25. So those are going to cancel, which means that x is going to equal ln of 13/3 minus 3, all divided by 0.25. You can type that all into your calculator. And it gives us exactly what Emmanuel said, which is x is approximately negative 6.1, what was it, 1347? 1347. X is approximately negative 6.1347. So there it is. There's our check step up here. Negative 6.1347. And just for fun, let's plug that in for x. So we're going to get 6. We're going to go with e to the x power. We're going to do 0.25. and then multiply by negative 6.1347, close that up, add 3. This should equal nearly exactly 26. Hey, look at that. Works out just fine. Cool. Questions here before we move on to the next one. Got another equation to solve. Actually, a couple more to solve, and then it looks like we got some inequalities, and then yeah, maybe we won't finish today. We'll see. Because then there's some, you know what, we'll finish the rest of this page and the next page, and then we'll do the calculator stuff tomorrow. Which should be a little bit simpler. If you remember how to use your calculators, that should be all right. Okay, number 5. Solving natural logarithmic equations. So here we've got ourselves 1/6 ln of 5x is equal to 2. So kind of like if you have an exponential equation, if you have a logarithmic equation, exponential equations, you want to isolate the power. Logarithmic equations, you want to isolate the logarithm, or in this case, the natural logarithm, the ln. And the natural logarithm here is ln of 5x. So what we want to do is get rid of the 1/6 that's multiplying by. Now we could use the power property of logarithms and say ln 5x to the 1/6 power, but we're not going to do that. We're going to go ahead and multiply both sides by 6 because that'll just get rid of the 1/6 over here and 2 times 6 over here. So those will cancel. And then on the right side, 2 times 6 is 12. So that'll be ln of 5x is equal to 12. And then from here, we can go ahead and just rewrite ln of 5x equals 12 in exponential form. And when we write it in exponential form, we end up with e to the ln of 5x is equal to e to the 12th power. And this is just like what we saw on the bottom of the previous page, but instead of having ln to an exponent, we now have e to an exponent of ln, which are still inverse operations. So base of e with an exponent of ln, those are inverse operations, which will leave us with the equivalent exponent here, 5x, and that's going to equal to 12 over here. So 5x is equal to e to the 12th power. All right, so then divide by 5 to get the x by itself. So we get e to the 12th power divided by 5. And that's all you have to do. Type that into your calculator. E to the 12th power divided by 5. What do we end up with? What is e to the 12th power divided by 5 to the nearest 10,000? Pretty big number, actually. What do we have? Anybody got it? 32,550 to the nearest 10,000th, we're looking at 9.9583. There you go. Okay. Questions about this one? Okay, let's keep going then. Apply functions with base E. So the next one here, it says that Newton's law of cooling relates the temperature of an object over time in relation to the initial temperature of the object and the temperature of its surroundings. The temperature in degrees Fahrenheit of a bowl of soup over time is modeled by this function, where T sub 0 is the temperature of the soup when it is taken off the heat source, so the initial temperature, basically. T sub A is the ambient temperature of the room, and T is the time in minutes. So basically what this is saying is that if you have anything that you place in a room, that object over time will come closer and closer to the actual temperature of the room. So if you have a piece of ice and you introduce it to a room temperature of like 65 degrees, eventually that ice will turn into water and come up to about 65 degrees. If you have a hot bowl of soup that's 160 degrees and the room temperature is 70 degrees, it's going to decrease down to about 70 degrees after a certain amount of time. And so what we're going to be doing here is we're not going to figure out how long it's going to take for that 200-degree soup to reach the room temperature of 72 degrees. What we're going to do is, what will the temperature of the soup be after 30 minutes? So, first question for you is, will the soup be more or less than 200 degrees after 30 minutes? Less, okay. Because it started at 200, the room temperature is 72, so the temperature should decrease over time. Will the temperature be more or less than 72 after 30 minutes? What do you think? Probably more. It certainly won't be less, right? If the room temperature is 72 degrees, the soup will not be less than 72. So our answer, before we even start this process, we know that our answer should be somewhere in between those two values. That's a really good place to start, because if you get a number that's outside of those, you can know for sure that something didn't go the way it needed to as you were working through this. So if we work through this, 200 degrees, that is our T sub 0 value. And this 72 degrees is our T sub A for ambient temperature. So T sub A. All right. Those are our two values that we're going to be using. And the T sub A ends up being in there a couple times. So first thing we're going to do, T of T, that's a little bit weird, but T stands for capital T temperature, lowercase t time in minutes. So we are looking for T of what? What are we putting in place of T, in place of the lowercase t? How many minutes? 30. So T of 30 is going to be equal to the ambient temperature of the room, 72 degrees, plus the initial temperature, which is what? What was the initial temperature of the soup when it was taken off the heat source? 200. All right. Minus 72 times e to the negative 32 multiplied by 30. Is there any like special logarithmic properties that we need to use for this problem? Are we solving for a variable at all here? No. You just type that into your calculator. Because the variable, like every variable over here has been accounted for. So there's no like natural logarithms or anything that we need to do on this one. All we have to do is plug in for 30 and plug in for the other values. So let's just type it all in, see what we get. So I'm going to type in 72 minus or plus parentheses 200 minus 72 multiplied by e to the negative 0.032 times 30. And so the ambient temperature, or not the ambient, but the temperature of the soup after 30 minutes should be about 121 degrees Fahrenheit. And that's exactly the number that we get here, 121. So approximately, so T of 30 is approximately 121. Cool. All you got to do is plug things in. Nothing really special about that. However, it looks like there's more. So we're going to continue this problem on the next page. I'm guessing there's going to be some logarithmic stuff to deal with. So let's flip this over. Actually, no, okay, yeah, maybe. Now that we have that, oh, this is the same problem. It goes all the way. All right, let's keep going with it then. So part B said, suppose a restaurant manager wants to make sure that the soup is at least 180 degrees when it is served to customers. Aha, at least. That's why we have an inequality here. At least means greater than or equal to. If the soup is initially at 200 degrees, the temperature of the restaurant is 72. How long from the time the soup is taken off the heat source should the server serve the soup? Okay, so now we're trying to figure out a time value. And the temperature should not drop below what when it's served? What does it say in this problem? 180. Okay, so it should not drop below 180 degrees. Now we have to do a little bit of natural logarithmic work here. Never thought that a server at a restaurant would have to use natural logarithms, huh? Honestly, they don't. But this would be a good way to find out. So, if we subtract 72 from both sides, again, we need to isolate our power here. So e to the negative 0.032t is what we're trying to get by itself before we apply any natural logarithms. So if we subtract 72 from both sides, what's 180 minus 72? What is it? 108? Yep. So 108. And what is 200 minus 72? We'll simplify at the same time. 200 minus 72. Oh, it's right here. 128. Okay. Then we're going to divide both sides by 128. So this is where I'm not a fan of how this problem continues or progresses. I would prefer, if I'm going to write 108 over 128, I'd prefer to keep that as fraction. The 128. I would rather have it as 27/32. That would be my preference. And as a decimal, it's 0.84375. Now that isn't a terrible decimal. It stops after 5 decimal places. So either way is fine. If I was doing this one on my own, though, I would probably keep it as a fraction of 27/32. But because it's a terminating decimal, it stops after 5 places, it's okay to write it as the decimal. My preference would be to write this as 108 over 128, which would then be reducing to 27/32. And I would probably keep it like that throughout the rest of the problem. However, it doesn't do it here, which is okay. There's nothing wrong with how this is being done. All right, so now we're looking at our isolated power, which means we now can apply the property of equality of logarithms. which means that the ln and the e are going to cancel each other out, which is going to leave us with the exponent, which is negative 0.032t. And so if you divide each side by negative 0.032, that will give us the answer. So let's get a fraction going here. And we are going to take the ln of 0.84375, and we're going to divide that by negative 0.032. And we're going to get, let's see, 5.31, 5.3. It doesn't actually tell us what to round it to. I'd probably do 5.31. So even though right down here it says 5.3. So that means that it should not sit for any more than 5.31 minutes. Now, 0.31 minutes, how many seconds is that? How many seconds is 0.31 minutes? How do you figure out how many seconds 0.31 minutes is? Multiply by 60. There's 60 seconds in a minute. 0.31 minutes multiplied by 60 seconds gives us how many seconds? About 18, yeah, 18.6. So 5 minutes, 18.6 seconds, which I would round to probably 19 seconds. But about 5 minutes and 19 seconds is that's how long it can sit before it needs to be served. Otherwise, it's too cold, right? That's the Goldilocks. This soup is too cold. Is she gonna send it back to the kitchen? You're really mad at the bears. No, nothing good happens. All right, last part of this problem. Now we're going to evaluate for t sub 0. So we need to figure out t sub 0, which is going to be the initial temperature of something. So we're going to be given ambient, we're going to be given amount of time, I'm assuming, and we're going to have to figure out what was the original temperature. So we'll probably be given the temperature after a certain amount of minutes as well. So let's see. Suppose a restaurant manager, here we go. Suppose a restaurant manager increases the temperature of the restaurant to 75 degrees. That's a warm restaurant. And he wants the servers to have at least 7 minutes. Wants the servers to have at least 7 minutes to serve the soup to the customers while the soup is 180 degrees or warmer. At what temperature will the soup have to be when it is initially taken off the heat source? Okay, so the ambient temperature then, T sub A, is 75. The temperature that it needs to be at least is 180 degrees. And it needs to be at least 180 degrees after how many minutes? 7. Okay. So lowercase t times 7. T sub t, or the temperature after 7 minutes, needs to be at least 180 degrees. We have a room temperature, ambient temperature of 75 degrees, and we need to figure out how warm it was to begin with in order for it to not cool below 180 degrees after 7 minutes of time. Okay, those are our parameters. Now, T sub t over here still needs to be at least 180 degrees. The room itself is 75 degrees. And this needs to be after 7 minutes of cooling. So this is all the stuff we got here. So this time, honestly, this problem is going to be a little bit simpler than the last one because this time our variable is not trapped up with an exponent. So we're not going to need to worry about using the natural logarithmic property of equality. We just need to isolate t sub 0. So the first thing we should probably do is subtract 75 from both sides. So 180 minus 75 is going to be 105. Because we're trying to isolate t sub 0. So that means we need to, get that 75 away. Then it says to use the distributive property. Honestly, no. I wouldn't use the distributive property here. I think that's a little bit clunky. It's certainly fine to do that. What do you think I would prefer here? Any guesses? Any thoughts as to what I would prefer to do here? Because I think it would take less time to solve it. So I'm going to go ahead and draw an arrow down to here because there's a way that I would prefer to solve this versus what's in the book. Again, the book does a perfectly fine job of solving it. I just don't really like it. I think there's a more efficient way to do it. Any thoughts? Because there's like 3 or 4 more steps written out here. We can solve this in 2 more steps, as opposed to like 4 more steps. Here's what I would do. What's that? No, we don't need to use natural logarithms at all in this problem because our variable is not trapped up with the exponent. By the way, negative 0.032 times 7 is negative 0.224, so they multiply the values in the exponent, so that's why that is. What I would do here is I would divide both sides by e to the negative 0.224. Because if we do that, those cancel, and then the only thing we're going to need to do after that is add 75 to both sides. It gets rid of the multiplication. I don't know why you distribute that e, because then you've got that e to the negative 0.224 in multiple places, which is more challenging than having it only in one place. So I would prefer just to do it this way. So this works. It's inefficient. I don't like it. We're going to get the same answer, and it's going to happen quicker. I don't know about you, but when I do math, I like to use the most efficient path that I can see. So we're going to get over here now, we're going to have 105 over e to the negative 0.224. We still have less than or equal to because we didn't multiply or divide by a negative number. And then that'll be t sub 0 minus 75. Then the only thing we have left to do is add 75 to both sides. Right? It's only 1 more step as opposed to like 3 more steps that you have to do if you do it the other way. So add 75. 75's cancel. And so we're going to get 105 divided by e to the negative 0.224 plus 75 is less than or equal to t sub 0. That's all we need to type in, as opposed to all this. It's the same thing, but this is a lot simpler, in my opinion, to do it this way. We still have a couple minutes left. Let's make sure we get this figured out. So math, fraction, 105 over e to the negative 0.224, scooted on over, plus 75. It should be the exact same answer, 206.4 degrees. There it is. It's the exact same answer. However, our fraction is a lot less complicated than what they had. I honestly don't know why they chose to distribute. That doesn't really make, it makes sense, but efficiency-wise, it doesn't make sense. So 206.4, it's the same thing. I feel like that's easier. I don't know about you, but I'd rather do it that way. Cool. That's it for today. We will finish up the second part of this lesson tomorrow.